Thank you.
All right. Welcome, everyone. Quite a crowd here. Very surprised to see so many attending a data conference. Like nowadays, everyone just tries to go to AI conference. I mean, we do have AI. It's Apache Iceberg, right? So kind of. But it's going to be about the data and how we should actually use data nowadays in analytical systems. A quick introduction of the community itself. So my name is Victor. I'm a co-founder of a company named Vacamo, and we created Lakekeeper. But that's later probably. The main part is what me and my co-founder made a decision last year that it's quite small amount of meetups about Apache Iceberg and data in Europe. And then we said like, okay, so what can we do? And should we just start something? And the main idea was, or the first idea was like, okay, we will start a meetup. And because we both were based in Germany, like let's start in Germany, and then, well, let's expand that and run the whole idea in Europe. And as you can see on the map already, we almost covered the half, or maybe more than half of European countries, and that's kind of the whole idea that we love to run the meetups in European countries. So last week I was in London, today in Amsterdam, then there's a meetup in Munich as well. We plan for the second half year as well. So the good thing for you is if you're interested in meetups like Apache Iceberg, you can attend. If you're interested to give a talk about Iceberg, feel free to apply and submit your session. So we have always 4 sessions, so you're free to attend that. And the good part is probably as well on Apache Iceberg, as you can see here, supporters, and you will probably find logos that do not really fit to each other, right? So, and the cool part is that you will find those companies in the same room. So you can find like Snowflake and Databricks sitting together and doing Apache Iceberg, because Iceberg is very inclusive. So it's not just as usual if Snowflake and Databricks or Google and Microsoft or Amazon in a room and in a blue buff. It's more like, okay, how we can actually enable everyone to use Apache Iceberg as a technology. So therefore, if you're interested and you want to host Iceberg meetup, let me know. So you will get on a supporter here logo list, and that would be awesome. Today we have actually 3 supporters. Xavier, thank you very much for providing the venue. Very, very kind of you. ClickHouse supporting us as well, and we the organizer of that meetup. We have actually 4 speakers. Well, I'm starting, and then we have 3 more speakers, and it's like in a concert, right? So at the beginning is someone who is not very important. It's just you have still time to go to bar and get your beer, and then stay till the end, because at the end you will get some kind of like cool presentation about Iceberg. And thank you for everyone who is going to be today and speaking and presenting, and kind of a motivation for everyone just to be the next time as a presenter as well. Well, starting with Lakekeeper and building the trust infrastructure. Well, in general, it's going to be about the governance. So something, you know, like usually when I speak to engineers and scientists, well, that's an important topic, but let's do it tomorrow, right? So it's some kind of a procrastination type of a topic, but it's getting more and more interesting, because what I get as a response from all that persona, well, if CISO data security is asking me, how did we do that results and who is reading that data, it's not that simple to answer. Yeah, so a quick introduction. My name is Victor. I'm co-founder of Vacamo. If you have like any questions afterwards to me, so reach out, use my email, my LinkedIn account. I'm happy to have a chat about Lakehouse, Iceberg, data, governance. Open source. That's quite interesting. Maybe to ask you, can you raise your hand if you use open source in your daily job? Like 99%. Can you raise your hand if you contribute to open source? It's not the same amount of hands, right? So what I want to actually motivate you on that slide is the contribution is not just writing the code because it's hard. The contribution can be like, okay, I will just go and then read the documentation, find the bug, maybe improve the documentation. I can go like run a test, do all that smaller things inside of that open source community. That is actually a cool stuff as well, or even like creating a meetup and run that for the community to get people together. So what you can see here on that slide, that's kind of like the communities where our company contributes: Trino, Data Fusion, Lakekeeper, Python, and mainly Iceberg. So I would say like our main contribution is an Iceberg Rust, because Lakekeeper is based on Rust, and it's how we actually contribute to Iceberg. Yeah, so I already talked about the Lakekeeper. It's Apache Iceberg REST catalog. It's REST catalog licensed Apache. It's not part of Apache Software Foundation, but if you want to use it, you can just take it and play around with that. And by the way, here's just QR code to the repo. If you want to become a contributor, scan the QR code, give us a star, and then you open source contributor. So next time you can raise your hand. All right, data time travel, Iceberg feature. As you know, probably we started 1990s, a little bit earlier, on building data warehouses. Nice monolithic box that could handle everything. Storage, compute, metadata, governance. So it was everything inside of that box. And it worked quite well, quite good. But unfortunately or luckily, 2000 internet happened, and we got like all the different data that did not fit inside of one box. And the solution was, okay, let's put multiple boxes together and call it massive parallel processing. Hadoop, Rimplum, all the different systems that helped us actually to manage the big data at that time, right? So the terabytes of data. Then cloud happened, and in cloud we got easy way actually to use a data warehouse like Snowflake, Redshift. But the cool part is that they started to decompose the monolith. So they said like, okay, we have a storage on one end and we have compute on other, and then I can store as much as I need. So I can store like petabytes of data, and then I can provision compute as much as I need for my kind of like query and use it. And that was quite cool at that time. Well, the big data community was saying like, oh, we can do that as well, and even better. So we're going to decompose monolith even further and make data as an additional independent tier, where you can say, oh, my data is now stored as a Parquet in open format, file format, and then I can move it in a place where I need that. Probably Databricks is one of the main players here. And that was for a while where we used to use Cloud Data Warehouse for more strict use cases where we needed transaction. A simple update, delete, or whatever with a Parquet was not possible because Parquet is immutable. In that case, we needed to go to Snowflake. And if you needed like petabyte scale, you would probably go like to Databricks and install Parquet and run all your analytics. So transaction schema evolution on Cloud Data Warehouse, scalability and ease of use on Data Lake. Well, that was kind of a limiting factor because the idea was how to get actually all in one, and it's how Iceberg actually came to a solution. And you will probably find other open table formats like Delta, Hoodie, and Iceberg. But we can say like from at least last year, Iceberg got like as a mainstream that everyone supports Iceberg. So you name a vendor or a technology, you will probably see that they do support Iceberg like a first-class citizenship, first-class citizen. And the cool part of Iceberg is that they made an additional decomposition of that monolith with meta as independent tier. So the whole information about the table, the structure, the data types now lives in an additional kind of like element inside of Iceberg. So which means now you can go and scale not just compute and storage and not just data, you can scale meta as well. And that is kind of a thing of Iceberg. By the way, can you raise like your hand if you use Iceberg? Okay. And your knowledge from 0 to 10, where 0, like I can say Iceberg, and 10, I'm like, can talk with Ryan Blue. Who is above 7? Good. So that question is not to you, Marco. So what is Iceberg, guys? What do you think? Any guesses?
I can just
Go ahead.
come up. I would say it's a self-library, so a library to manipulate files,
Okay.
or file storage to support the AC transaction types.
Yeah.
All the things around it, like metadata management and maybe compaction as well, so to maintenance and so on.
That would be wonderful if that would be the case, right? So unfortunately, Iceberg is this. It's a specification how that can be done. And then we have a specification and wishes from a community, so you can actually go and build that stuff. The compaction and whatever you want. You can build all the different implementation. I mean, there is a Java implementation, but at the end of the day, you will build that. So not by the community. So what my company started to build is a REST catalog specification. It's where Laykeeper actually sits. But then there are different specifications around that define Iceberg. Yeah, a famous one is going to be obsolete quite soon, I guess, through V4. We're not going to have the same structure, but that's actually what I described to you. So we have a data, we have a metadata, and that's like 2 different independent layer. And at top, we have a catalog that actually manages the whole part of that. And maybe a very quick evolution at the beginning before REST specification. We had a couple of different catalogs with different implementation, which was hard to adopt Iceberg because every client needed to implement that type of catalog. And then we got the REST specification that actually explains every one client and server how to behave and to read and write Iceberg. And that was kind of relief in order to adopt the Iceberg. So 2022, we got the REST specification catalog. Was confusing because, well, we have already data hub catalog of that catalog, and we needed to explain it's a different catalog. Then we moved to a more like meta store. So now we have monitoring, a little of governance. And nowadays we actually speak more on a control plane that helps us to manage trust on our lakehouse. Here's Lakekeeper that actually can be used in that sense that you have your data stored in every cloud, and then you can take every engine and read the data. But the main part of a Lakekeeper is that you have table management when you have like a DML statement, you have fine-grained access control, and some governance elements. So now we know what Iceberg is. So what Apache Iceberg actually did solve. Let me make that easy. It's late, I understand. Sorry? It is on-prem, it is in the cloud, but what mainly it solved its interoperability. So that's the first time in our data history that now you have like a format. Well, you can argue CC was probably the version 1, but now you don't need like a Postgres and store in a Postgres, but then you need, and then you will say like, oh, I have Oracle and I want to read the data from a Postgres, which was like a migration project for you, or like you want to use the data in Oracle in your SQL server. But right now is what actually happened. Now you store that Iceberg in that single universal format, and then you can use all of that technologies to go and read the Iceberg. So it's very, very interoperable. That's probably the main thing what Iceberg solved.
For example, if others use data containers.
Delta?
Yeah.
Yes.
Can they also claim that they solve interoperability?
In a sense, yes.
Yeah.
So it's why open table formats like Hoodie, Delta, and Iceberg, they solved interoperability.
So it's not advantage of or what Iceberg brings to the team. It's not the thing that Iceberg solves because it has been solved before by others.
Yeah, by CSV already as well. I think CSV solved that as well. But the Iceberg itself, like the main advantage of using Iceberg is to solve interoperability. And what Delta does not bring to you, Delta is more or less controlled by Databricks. And if you want to use Iceberg, you can provide the whole service with Iceberg. You can actually contribute to Iceberg and build your own feature. So Iceberg is way more versatile in a way how to solve interoperability than Delta. Yeah. But if you like Delta, I'm not here in a. It's not a charge. Whatever you pray for, it's all good. So the question is like what it solved, but then the question is what it did not solve.
Interoperability could be good for here as well, because in many sense it solves problem of interoperability between well-known technologies. But if we want to have other type of niche technologies and want to integrations, want to have lineage, then we need to have very good metadata. And I am not sure maybe you have it. And that one I believe is not so.
Well, lineage is probably a good thing, but I would say it's not about the lineage, it's about the governance. So we still have like the way, even the niche technologies, I don't know like exactly if you have Haskell or Elixir, it might not able to read, I don't know. But starting from Python, Go, C++, Rust, Java, all of them can read Iceberg. And all the different companies are able to read. So you will take probably like 80% out there can do that. But what is not solved is governance, because that was not part of the spec. We don't have like a governance spec. And therefore it's like, okay, so how are we gonna actually do that you know who is reading, who is writing? And unfortunately what happened, every one of them started to build a proprietary way of a governance inside of their catalog, because as you saw, catalog is in the middle, and then you need to somehow to go through the catalog, and then they all started to build a governance what they actually knew at that time. And if you will look at that governance, it's quite biased, I would say. The idea is on our end is like, okay, so how we can actually do that better? So on a Lakekeeper, we said we don't want to trap the governance. We want to follow the open standards on the governance and solve it in a different way. So you don't need to be very concentrated on the governance, how it's solved in Databricks. I mean, if you're in that single bubble, you can just go with Unity, all is good. But if you're in a company that uses all of them, and there are plenty of companies that uses all that technologies and even more, so what you can do actually, you can just offload the governance to a single place that can do it. But it's better done in a way that is more standardized. So what we actually did with Lakekeeper, so Lakekeeper, you can run it as of now, like on your machine, on your laptop, or on your Kubernetes. And the first decision what we made is that Lakekeeper as a catalog is never the IDP. So we're not going to issue you a personal access token. And it's very important, because if your employee will leave the company, you know, like something happened, and the personal access token lives for the next 90 days, you probably don't want to be in a situation that someone is able to still read the data. Or access key and secret key still available, right? So it's easier way. Your identity is one place, and it's going to be switched off, and then everyone who touches that identity is not able actually to use it anymore. And the second thing is that the governance itself. So what can I actually read? So the governance tuple, right? So the object, like table, then the action read, and the person, the principal, like Alice or Bob, is stored outside of Lakekeeper as well. So the definition and storage is outside of Lakekeeper. Lakekeeper is actually only the execution of that specific policy. And finally, what we have on Iceberg as well, there is a special thing about the compute. We have two types of compute, a general compute. So it's a single service principal that goes and reads the data. And usually you have like client ID, client secret for that service principal, and it's all fine. But then you have all that funny multi-user systems where the connection to catalog and to data is done by a single technical user that can do everything, but then you need to understand who runs that query. Is it run by Alice or Bob? Do I need somehow to react on that? And to solve this problem, we use another open source technology, the Open Policy Agent, that uses like a bridge. So Trino is able actually to go and get the information from OpenSSH without breaching. So we can actually help the multi-user systems to get the information and solve the governance. So here is an example of Lakehouse based on Iceberg, license-free, cutting edge. You can just take it, deploy it, and use it. Quite interesting. But talk is cheap. Show me the code, right? So probably just to quote Linus. So I brought a demo, and if you want to run that demo, it's all open source here on our repo. It's folder examples, and in that folder there are different examples, and I will use the access control advanced that provisions the whole environment what I just showed you, but you need just to run the Docker Compose app. You don't need Kubernetes for this. And if it's up and running, you will get actually first the Jupyter notebook. So you need to bootstrap Lakekeeper. Then you need to create the first warehouse. And then we need to create the catalog inside of Trino cluster. And afterwards, you can actually go and read the data. And in my case, he's a Peter. And Peter won't just read a table products from namespace finance. And it's quite easy for Peter, I hope. So it's Peter and password is Iceberg. And voila, Peter is able actually to go and read the table. Now what I want to simulate is a user Anna. So I'm taking just an incognito mode just to have a different session. And now we'll run the same query for Anna. Make the authentication for Anna. And we will get a permission denied. So that's exactly the state what inside of like normal company you want to get, that the role-based access control or whatever is in place and enforced. And it's quite a challenge because if you saw the slide before, so you have like different technologies flying around, all decoupled. So it's not a single nice monolith Postgres that can handle everything for you. You need to think about how to implement that. So what now Anna can actually do, if Anna will try to go to Lakekeeper, sign in, we'll get access pending, nothing to see now. But she can call Peter and ask for the access. And now Peter here can go to warehouse, demo, finance, tables. We have two tables, products. Let's take products, permission, and grant Anna a select access. So on Anna's side, here is Anna. And now Anna can actually go to warehouse, demo, finance, tables, and she's only one table, the products, not both tables. And same if the request here in Jupyter on Trino will be repeated. Now Anna can see the data. So that's kind of like, looks very, I understand, boring and simple, but in a Lakehouse way, it's quite challenging to accomplish something like that. So getting back to the slide. Yeah. So then we got a feedback like, guys, like count all the technologies. It's way too much to manage. And it's why we took a different approach with CETA policies. Someone heard about CEDA policy? 1, 2, 3. Invented by?
AWS.
Yes. Unbelievable, right? So Amazon Web Services do make some open source stuff. And it's quite amazing thing what they developed here with the CEDA policy based on Rust. For us, super easy just to integrate in the Lakekeeper. But the cool part is that you will define the policy even upfront. You don't need to have a data in your lakehouse. You can define the policy. It can be defined by your CISO, data security guy, or even better, by the data owner. You know, like we always looking for the data owner. We'll say like, oh, there's a table. That table is gonna be accessible. Make a policy for that. And this is a declarative approach. So it's not imperative approach where you need to click inside of UI. You can just go actually and build a declarative approach and use it as permissionless code, because you will develop that, put it in your Git, and then there is an action that moves that to the next stage, and you can actually build the whole stuff more or less with security checks and kind of approvals and workflows and whatever you have like inside of your company, because sometimes it's very, very complex. If you look like at banking, on insurance, or like high regulated companies, it's quite hard to get the part of security here. So, but why to do something like that? It's because we want to achieve a zero trust. And zero trust is quite simple in the definition, but hard to achieve. That on a zero trust, we want to check like every request with a least privilege, and we don't want to have a password that lives forever. You know, like, oh yes, admin and admin 123, and that password can be used and can read everything. So that's not a zero trust. And if you have a breach, then the breach is not like for everything, but maybe for a single table or even for part of the table. And it's the idea of a zero trust. And that's exactly what we're trying to achieve through permissionless code with CEDA policies. But to explain you like more in a human language, why to go that path, you probably have heard about separation of powers. That's something what we leave, right? So it's something what we like, and we don't like dictatorship, a single instance that can dictate, define, execute, and all of that stuff. And same is for the zero trust and governance and data security. So what you can think about, we have a legislative where the bills are defined. So it's where we will define our policy. And that policy will version and move to actually to the next stage, to executive, like execution, like Lakekeeper catalog, where that policy will be applied. Same like what we have like in our system. And then we have observability, it's what we call, or judicial, where we will collect all that information, we'll make the judgment. Was it good? Was it not good? Do we need to go back to legislative and tell them, guys, please change that policy because it's not good. You may make some kind of bad things. And that's kind of like the whole idea what we developed with Lakekeeper. So we don't want to be like the single thing that controls everything. We want to be just maybe like executive, and then you have some different places inside of your company that defining the policy or evaluating their policies. And the whole idea is just to make peace, because, you know, like if you have all that different wars inside of governance, that's not a good thing, because you're not concentrating on providing value inside of your company. The idea is like to actually make that a little bit different, that, for instance, SAP can concentrate on the business stuff, Snowflake on analytics, Databricks on data science. Well, I don't know what about the Fabric. If you know, let me know. Microsoft, all good. Yeah, so that's idea of a piece, but there is a different solution. It's a Switzerland solution. So if you don't like separation of power, you can put everything inside of a neutral field and have your wars inside of your solutions as well. So there's kind of like the way for everyone. It's up to you to make a decision here. Takeaways. So Iceberg won the interoperability, and we can have a discussion if you have like a different opinion. And from my perspective, the governance is the next battle, and we can solve that in different ways. And a separation of power, and a Switzerland type of solution, on a dictatorship solution as well. The catalog is the control plane that allows you actually to do more stuff than just create a table statement. Governance is in a zero trust and only through enforced. If you have it as a code, because you need automation, then today you have maybe 100 users. Tomorrow you have 100,000 of agents that you need somehow to manage. Yeah, and we claim that Lakekeeper is a neutral ground. That's kind of like our idea. That's it from my side, guys. Thank you very much. If you have like any questions, I can take them. Yes.
I was wondering, because you are not showing field access control.
Yeah.
Do you also have some robot access control? Because I feel like this is a bit harder with the way Iceberg kind of works.
Yes, it was yesterday, kind of more or less agreed in the community to have a read restrictions. So I think it will take now a couple of months to get there, but the raw level, color masking and raw filtering is coming.
Okay. Do you know how you would implement that? Because you're kind of defending credentials. Now you have maybe the 2 rows, one is filtered, one is not filtered in the same parquet file.
Yes.
Now would the catalog have to do all the filtering themselves?
No. Do you remember the picture with trusted compute?
Yeah.
So we will rely on that part. So you inside of your company will define, okay, that's a trusted compute, because we know they're going to apply that restrictions. And if you, from your laptop running with your DuckDB and you want to connect, the catalog will tell you you're not a trusted compute, so you don't have like any access to that table. Good. Other questions? Not the case. Last chance to become open source contributor, guys. Thank you very much. Sure.
So you will see this, right? On the, yeah. Slideshow. Is that correct now? It maybe is synchronizing. Is that correct? Yeah? Okay. Good. I would like to, my name is Daryl Ronald. I'm from Zebia. I'm a data engineer, data platform engineer. My colleague, Julian de Ruiter, in the front row here, has worked with me and a team that we're going to show you an innovation project we developed internally that's now going to market. And it's built on Iceberg and Lakekeeper, which is why it's appropriate for tonight. This is not a sales pitch. We're trying to show you, like, how did we build this? How complicated was it? As you know, so just a word or two about CB, because you're in our one of our training spaces and event spaces. We're over 6,000 in many offices. We started here in the Netherlands in Hilversum area in 2001. We really strive for authority in what we do, so we give a lot of trainings as well. We are in the data and AI cell. We have an office in Oostenburg, close to the central station. And we're going to show Project Datalist, which is part of our internal innovation. We have a budget for innovation, plus we have innovation days like once a month. And these are just some examples of our output. One thing that's important, and also to speak about the event tonight, we have a lot of partnerships. We are kind of vendor neutral. We have recently, about a year ago, we started to dive much more into European cloud. So we have recently announced partnerships with OVH and Scaleway, now with Mistral. And what we're going to talk about tonight is digital sovereignty. So sovereignty is a bit of a marketing term. Essentially means everything around portability, control, transparency, etc. We have some slides on that. At the moment, nobody is sovereign. Nobody can be sovereign. It's a global world. Technology is global. Chips are global. So it's always on a spectrum of 0 to probably 80% of sovereignty. The closest countries get are people like US and China. So when we talk about sovereignty, what we want to talk about tonight and why we have this project is our clients need it. Companies need it. Regulation is arriving. So you have to control where your data lives and how it's computed. You need to be able to move data and workloads across clouds for resiliency and governance. You need transparency in what is the technology stack you're using. You need to comply with EU regulations. So we have lots of clients in government, in banking, healthcare, and they have to follow EU regulations. And of course, vendor lock-in is a big issue. You might have seen this. The European Commission has talked a lot also in the past week, an entire digital strategy. Of this, there's a sovereignty framework. So these are some of the 4 of the roughly 8, I think, that we are focusing on and that are part of the story that what we're building here tonight. So sovereign data platform, we also call it an open data platform or an independent data platform. It's extremely hard to build, right? So you have Snowflake, you have Databricks, but you don't have a lot of open source projects that tie this all together. There's a lot of glue, there's a lot of work with authentication, etc. So companies do not take this on themselves. This is something they buy, or hopefully we can provide. So clients come to us and this is our solution, is we had looked in the market. So we looked at European cloud providers. Does anybody offer a data platform? OVH, an interesting company from France. I'm not sure if you know them. They have an internal data platform, but it's not GitOps. It's not infrastructure as code. So it mostly works if you want to do ClickOps. Wasn't good for us. Stackable is an interesting open source project. I think it started in Germany. Also didn't work for us because of the tech stack. So what we did is we assembled a team and we built it ourselves. And that's what we want to show you tonight. We have code contributors, project contributors. Julian and myself are here. It's a team effort and there's a lot of applications. It's very hard to master them all, but we do have a good picture and everybody in the team is contributing something different. So a little bit on the why and how. So if you want to control your compute on your storage, we support out of the box DuckDB and Trino. Spark is an optional at this point. We've kind of proposed a tech stack which is very opinionated. Portability, so we work with Kubernetes clusters. We can basically run it anywhere. We are going to do a series of deployments to show our clients, like OVH, GCP even, because it's still an interesting product, even if you want to move away from one of the big commercial products. Enterprise open source, so we focused a lot on having fine-grained access control. Right, so if you're a hospital or banking, you need, you have a lot of PII information, you need to mask by column and row. So that's something that we had to support in this. So using things like OpenFGA, Open Policy, what was it? Open Policy Access Agent. So some of these you will see, actually what was just presented by Victor, are used and built in a full deployment here. So the opinionated tech stack that is composable, these are basically a lot of Helm charts and stuff that are running and being deployed. We have Kubernetes running on the base, Argo CD as GitOps and synchronizing the Git state with the applications. We use MinIO temporarily. We want CWDFS, you know this, it's a work in progress. So CWDFS is it's a CNCF project, is it not, I think? An open source object storage. So we want to replace MinIO. There is some controversy about MinIO. We have observability. We have security with Authentic. We probably will switch it out to Keycloak, which was also used in your example. We have Airflow for orchestration. Lakekeeper is the catalog and metastore. Longhorn and Iceberg, they're working under the hood. And then we have different applications for dashboarding, so Superset, and we have Jupyter Hub, which you can launch VS Code instance, Marimo, Jupyter Lab, and we have open metadata. I just want to pass over this, like we've developed the platform with certain use cases in mind, right? So every client and company has, you know, your data engineers, analytics engineers, platform engineers, and data managers, governance people. So I'll kind of show with some videos how you would walk through what are the applications that each of these people are using. So it all starts with a portal. This is your kind of entry point, your glue, structured around some kind of use cases. And this is it in action. So very simple, but it's a familiar interface. It's a perfect starting point. This is your launch pad with your different applications. We have extensive documentation already built that explain both from a use case point of view, a persona, and developers building on the platform. Then we have Lakekeeper, which you've also just seen. Here we've deployed the Java shop because an analytics engineer is one of the main users of a data platform. And they're the starting point of how we're testing this and building this. What is the first use case? So we have a Java shop. Does anybody know Java shop from DBT projects, right? It's your, so Java shop is like what DBT provides you as out-of-the-box data sets. It's a sandwich shop in Australia. So from this, you kind of get a small data set that you can query, and you can basically test all the functionality of like running it in Airflow as a DBT job so that you get all your analytics output. This is MinIO object store. So at the moment, what's interesting is because this is all open source, you kind of have our little portal that is an entry point. And from there, you have all of the very detailed interfaces. You can think, well, it's a bit of a aesthetic clash or use case clash jumping between the interfaces. Maybe with time we reskin and develop a bit more, but then you're going really towards full product and saying, well, we're going to compete with Databricks, right? But so out of the box, you have all the features that each of these individual products offer. This video is a little bit longer, but I thought, well, maybe it's interesting that you see the walkthrough of everything. So of the people here, how many are like data engineers? 1, 2, 3. Data scientist, data analyst? Yeah. Platform engineer? Okay, so it's a bit of a mix. You have kind of everyone. So try and imagine how you would interact with this. This is a bit the data engineer type role, bringing data in. So this is Airflow. Maybe some of you know it. This is how you orchestrate, schedule jobs. Each of these is a node in a DAG. And in this case, what we do is a simple DBT build, right? So your analytics engineers have a DBT project. We schedule it to run in production every day or 5 times a day, whatever we want. So very detailed. There are some competitors like Dagster, some other open source, Orchestra. Not all of them are products that we could use here. Airflow is an industry standard. I'll skip to Trino. So we use this. We have a combination of DuckDB and Trino. Trino is used especially for any of the compute that is running on the different user pods with notebooks, Superset. They will query. Trino will filter all of those into Lakekeeper and pass the credentials down. So we've organized everything based on user groups, but you can also give extra attributes where you then have very fine-grained access to say, well, this column is always masked. But so now this is all running through, let's say, you're a data engineer or you're a data analyst. And so the whole platform is organized, your access around these user groups. And that's something that is contained in Authentic. Then we have the Explore. So you have Jupyter Hub here. You can start a notebook in Jupyter Lab, Marimo, or Code Server. In this case, we have some examples where you can
change your compute size. It launches up a Kubernetes node for you. And in that, all of the authentication and authorization is passed from here through Lakekeeper onto the object store. So the authorization is one of the hardest things to get right in this, right? This is the key glue that if you're an enterprise user, you are ensured that the governance basically is working across the entire stack. So this is a very simple one. I had some other demos, but I think I lost them. So keep it, this is very simple, but it's at least that you see, has anybody worked with Marimo? Or Marimo, yeah. So it's it's a very interesting product. It's one of the main early developers. It's actually based here in Amsterdam. And it is, it's not like Jupyter Lab where you run cell by cell. You can have it all running at the exact same time. It's very interesting for that. So it's very interactive compared to you change one cell and it'll populate across all the cells at the same time. Superset is an open source dashboarding. So you have dashboards, charts, data sets, and query. So here you have a SQL lab. And this is your open source replacement for things like Tableau, Power BI. And it's quite incredible. This is a very low-tech dashboard. This is just querying some of the Jaffle shop, right? So it says, well, we have 2 stores, and they are X percentage of our sales. These are our most famous, our most popular sandwiches. And it's very easy and interactive to build dashboards with this. It's quite, I think, far better than something like Power BI. You have interactive queries built in where you can select your database, your schema. This is all running with Trino compute. Here's some simple outputs. And from here, you can build a data set, which then you can bring in and use here. So you would basically connect this chart with one of the data sets. And then last, you have open metadata. So this is your governance layer. This is not an extremely developed one, but essentially you work with domains and governments. You can show your data assets here, which is linked with the Iceberg. And you will also show lineage. In this case, we only have one layer of data tables, so the lineage is very flat. But if you would build up an elaborate DBT project, you would see the tables filtering all the way down. And when you join tables, etc. So this is quite a powerful tool. It's one of the main open source products. And then I talk a little bit about, for those who, has anybody been responsible for Kubernetes within their teams or orgs? Yeah, so we have, what's interesting here is just to say this is about portability. So we work with our Xebia Cloud colleagues. Originally, we developed a lot of this ourselves, and it was very slow and painful because we were figuring out a bit too much on our own. We now work with Xebia Cloud to develop, they have blueprints which they can deploy on basically any scenario. So on-prem bare metal servers, working with an open cloud stack as a private cloud. We can use European cloud, hyperscaler cloud, does not matter. And from there, we can just put Dataless on top of Kubernetes. So the portability is there. It's quite powerful. This is a little bit about, end users don't see this. This is a bit about the platform engineering aspects of how you would interact with Dataless. So Argo CD, this is showing you all we have 29 applications running. This is a lot of layers. This will sync with your Git repo, right? So this will mirror what you have in Git in production. You can see each of the applications and all the different services that are running. You can see when it's synced, when it's out of sync. You can relaunch. You can kill pods and bring them back up. And after this, we also set up your Grafana, Prometheus, Loki for capturing your logs, for your watching your CPU usage in the cluster. And it sorts by all your different applications. You can, as you probably know, you can monitor everything. So this is something that would in the end be set up in the environment you deploy this based on what you really want to capture. You can capture way, way, way too much if you want. But so a complete observability stack as well as the data platform. A little bit about technical decisions. So on the topic of data catalog and Metastore, we had a number of years ago, we used Unity Catalog to create a product called Duck Lake. In the end, that was recently, the name was taken by Duck Labs. They're now called Duck Labs, DuckDB Labs. But we had built something very similar internally. And we realized that Unity Catalog is not a completely open source product. It was not developing as fast as something like Iceberg, Polaris. And so we had written that off. We looked at Lakekeeper and Polaris. Some of the strengths of Polaris is, it's a lot of developers. Some of the weakness is that it's not as much fine-grained access control as something like Lakekeeper. And we really liked how you had the authentication and authorization built into Lakekeeper. That was actually quite important for us. It made our jobs a lot easier. We started out, so if you notice, there was, in the slides earlier, you had showed how it started with OpenFGA and OPA, and then you replaced it with Cedar. So Cedar you actually have to pay for, but it's like then less services for us to manage, right? Like you just kind of, you have a question?
Yeah, I'm curious. You just mentioned Duck Lake. Any reason you didn't want to go with Duck Lake instead of Iceberg?
Well, so we had started this in the very first hackathon we did was in December, and I think Duck Lake was only just released, like it was not ready for this. They also didn't have any of the governance layer. We would have had to build that entirely on our own. And they didn't have multi-user at that point. And like now they have Quack, which potentially could be something we work with. So it is nicer in that you don't have all the Metastore, right? Like that was its main selling point, which is great. But it would create a lot of other problems for us. Maybe in the future it is an option, but right now it's not. But yeah, good question.
Thanks.
So in the end, we went with Lakekeeper. This is a little bit to talk about the complexity of how things are working, right? Like when you start to glue all these surfaces together, right? Starts to see the secret sauce, right? So you have these solid lines and dashed lines. So data crests are moving through as solid lines, and the dashed arrows are, what do you say, sitting outside the query path. So in some of these we use DuckDB, but in some we use Trino, and this is basically for this issue of Trino can absorb multiple queries. We don't have to push the compute into each of the pods, and the authorization worked more easily. But this is one of the more complex things. And if you zoom into, this is like an example of an anatomy of a superset query. Julian, if you have questions, you can ask Julian, because this is his mermaid diagram. He wrestled with this. But essentially, if you're a user, you come in here, then you have superset, then you have your authentic, which is your main SSO login. Then you have Trino, which is managing the query. It goes through the OPA sidecar. So this is OPA because Cedar is not implemented here. Then it goes through Lakekeeper. Then it goes through OpenFGA, so your fine-grained access control on your object store. And then you get the MinIO object store, and then it comes all the way back to you. So this is the complexity of one of the biggest complexities of the system. So with that, yeah, thanks, and happy to answer any questions at the break or now. Yes.
Great work. Thank you very much for sharing. I just had a chat with my friend today. He's developing something like that. But anyway, so you are providing so many tools Is it, have you, say, or
I guess I start. All right, guys. So now we have Marco as the next speaker. So take a seat. And let's. Stage is yours.
All right, thanks. So yeah, I'm going to talk about Iceberg in Postgres. So my background is mostly in the Postgres space. I've been working in particular on Postgres extensions for the last 12 years. First at a company called Citus Data on a Citus extension that sharded Postgres that was acquired by Microsoft, and I built other extensions there like PG Document DB. And then I was sick of large companies, so I went to a small company, Crunchy Data, and started working on a new project that I'm going to talk about. And then last year, we got acquired by a bigger company again, Snowflake, but not quite as big as Microsoft, so it's a lot better. Basically, the project I'm going to talk about is called PG Lake. This is a project we open sourced last November, and it's kind of based on what we were doing at Crunchy Data. And it implements, well, two main things: the ability to query, import, and export files in object storage directly from Postgres via regular SQL commands that you send to a Postgres server. And it lets you access Iceberg tables and manage, like create Iceberg tables and update them, change their schema directly from Postgres. And there's two reasons why you might want to do that. One is the way Iceberg is the way we implemented Iceberg means that analytical queries on Iceberg tables, even though it is from Postgres, are usually a lot faster than those same queries on the same data on Postgres tables, because we're able to delegate these queries into DuckDB, which is sort of embedded into PG Lake. And the second thing is the interoperability. So it is actually very useful to to be able to do transactions across Postgres tables and Iceberg tables as a way to bring data into other systems or consume data from other systems. And I'll show you some examples of why that's actually a very nice pattern. So if you want to see the source code or use it, it's at Snowflake Labs /PG_Lake. Postgres extensions are just always called PG underscore something. So PG Lake is an extension, so it's kind of like a module that you'll load into Postgres. It's not a Postgres fork. It doesn't change any Postgres source code, but Postgres is all these little hooks that we can use to manipulate its behavior, to add new behavior that isn't in the core system. So some of the things that PG Lake, or that become available when you add PG Lake, is that you could create a table directly from a file. Could be in S3 or Azure Blob Storage or just a URL. And it'll go and figure out what this file looks like. It'll do some like sampling. It'll figure out what from the header, what the column name should be, what the type should be from the sample, and it will just create the table directly for you. You can also then load new data into the table directly from a CSV file or a JSON file. It even supports like some exotic formats like .zip shape files and some geospatial formats. Now, if you just have a lot of data sitting in S3 and you want to be able to query it, you can also create a foreign table, so then you don't load it into Postgres. It just sits there. You can run queries on it. And you can also just run a Postgres query and then write that into object storage, which is very interesting because now you can kind of consume data from object storage and write it back. Yeah.
You mentioned that you're embedding the DB. All this part of DB as well?
Yeah. That's a lot of the, especially for the file interactions. Yeah. Ultimately, a lot of like CSV sniffing is something DuckDB does particularly well.
Are you using DuckDB internally, or have you built your own kind of wrap around DB?
Yeah, we've built our own. Actually, another former Citus colleague, he went to MotherDuck and built PGDuckDB. So he, yeah, no, I know Yelta very well. I met him 2 days ago. And the other thing you can do it was probably the most interesting feature, is you can create a table using Iceberg. And you can insert into it, update it, do schema changes, and do transactions. And so we started this project about already 2.5 years ago when I joined Crunchy Data together with 2 longtime colleagues. And then I think our original goal was really to make Postgres more competitive as an analytics engine, because what we saw in the past is that a lot of companies, they get started on Postgres. It's kind of the logical choice for your operational database. Some companies start growing really fast. Lots of data start going into their database, and they start having new requirements of like, what are people doing with our product? So they start running analytical queries, and things get very slow. Maybe make some read replicas, but then the read replicas also get slow. And so then you kind of start thinking about migration to an analytical database. So we thought, can we actually make that much easier and just say, hey, you can have Postgres, but fast as an analytical database. And we did that using Iceberg, because at the time that was sort of up and coming. It wasn't quite clear, it wasn't settled whether it was Delta or Iceberg going to be the main table format. But it was sort of very nicely defined. It had some properties we really liked. So we used that as a kind of a storage format for fast analytics. Of course, it had the interoperability benefit, but we weren't so focused on that at the time. But then a few months later, we got acquired by Snowflake. Now, Snowflake didn't really need another data warehouse. Their main one is pretty good. But where this work became very useful is as an interoperability layer between Postgres and Snowflake especially. And so we did open source the project last November, and Snowflake now has a Postgres service. So we've been kind of deeply integrating it into there and using it for all sorts of integrations with Snowflake. So the basic idea with PG Lake is that indeed a lot of the operations are kind of delegated into DuckDB. Postgres and DuckDB both have this notion of extensions where you add more feature to the core system. And so we have actually a combination of DuckDB extensions and Postgres extensions to kind of create a very smooth integration in the end. And so something you can do in Postgres is there's all these little, they call them hooks. They're basically function pointers. Postgres is written in C. Most of the extensions are written in C or in Rust. And so you can, when a DDL command comes into Postgres, it gets parsed, and then the extension gets a chance to do something with the DDL command. For example, we can look at a copy command, see if there's S3 in there, and then do make those commands go through our logic, which maybe ultimately does something with DuckDB. Or if there's no S3 in there, we give it back to Postgres. Like the extension can really break Postgres. So it's also a bit of a responsibility to write extensions because you can easily break this, mission critical operational database. And it also provides lots of different ways to hook into the query planner, the query optimizer, so we can change the way queries are executed under the covers. And so that lets us do a lot of different optimizations. Now, one thing about Postgres is it is very old, and it has a process-based architecture. What it means is every connection that you make to a Postgres server spawns a new process that's kind of somewhat isolated from the other processes. The 1987, I think, Stonebreaker paper on Postgres said that they're going to fix that pretty quickly. It's just that not all operating system supports threads yet. So let's see when that happens. But that means that you probably shouldn't run DuckDB in every PG process, because every DuckDB instance is going to want really a lot of memory, its own thread pool. So what we ended up doing is actually running a separate server process that has a single DuckDB instance with one thread pool, one buffer pool. And then all the Postgres sessions, all the processes are connecting to that one process. And they actually use the Postgres protocol, but it's sort of internal to the machine. It's just that Postgres already has a very good built-in Postgres library, so it was kind of an easy thing to use. And then, so DuckDB we mostly use for interactions with S3 or Azure. And we extended DuckDB a little bit to have a file cache. So all the Parquet files that we read will sit on a local NVMe drive usually. And then Iceberg is kind of fully implemented in Postgres. And we actually really re-implemented Iceberg from scratch. We're not using DuckDB Iceberg or any existing libraries. There also weren't that many yet when we started. But one of the things that lets us do is integrate really carefully with everything that Postgres already does. And basically, well, we've seen this picture before. What we wanted is you can just connect to Postgres, you can create an Iceberg table, and you can start using it. That should be it. And so in Iceberg, you usually have a catalog, and a catalog essentially, like underneath, one of the important things about the catalog is that there's a database that can do transactions, and that database stores the current location of the latest metadata file. And if the database rolls back, then the transaction on Iceberg rolls back. But in our case, we're doing everything in Postgres. So a sort of natural thing for us to say is, well, Postgres is the catalog. It's also the query engine. So you have kind of one box that does both of these things. Well, it's query engine from the client perspective. Internally, a lot of the queries are handled via DuckDB. But so if you write to an Iceberg table via Postgres, it'll start producing all the metadata files and manifest files and Parquet files via DuckDB, and then it just updates an internal table that says, here's the latest version of the table. And so we actually, it's a fairly comprehensive implementation at this point. So apart from transactions, there's, we're borrowing some things from DuckDB where you can scan Parquet files, even if they're not in cache. It can do like parallel range requests. It can do parallel multi-part uploads. For updates, we kind of switch between this notion of merge on read, where you write files that contain the offsets of the deleted rows, or we rewrite the file if there's too many of those. There's also auto compaction. So every 10 minutes, Postgres will take small Parquet files and smash them together. There's a lot of query optimization. So, well, DuckDB is pretty fast, but then part of the challenge is like delegating as much of the query as possible into DuckDB, doing file pruning, using the caching effectively. There's Iceberg partitioning, so you can partition by time and different columns, which helps with performance, also makes, for example, deletion very fast, because if you do delete less than 2026, it'll just do a metadata-only operation, throw all the old partitions away. And then on the Postgres side, we basically try to make sure that every Postgres feature works. I know you've used Citus in the past, and one of the challenges we always had there is that we didn't quite have full SQL support. And so we sort of from day one, we said, okay, we're not going to do that, make that mistake again. Everything should work. Views should work, sub-transactions should work, stored procedures should work, everything should work from day one. And by just deeply embedding into Postgres, we were able to do that. The only thing you cannot do is like indexes and foreign keys. Yeah.
The local for Postgres on rises to the very small updates, inserts, and so on. Do you write this directly to Iceberg, or do you somehow cache it somewhere so that you get bigger facts?
No, I mean, like you can make a choice as a user for this table is going to be a Postgres table. It has fast updates, and this table is going to be an Iceberg table. It is, can be infinitely large, but an insert is going to take a few hundred milliseconds. And then a common pattern is to take batches of rows from a Postgres table and put it into an Iceberg table, for example. I'll show some more of that. So yeah, you basically use it where you do create table, pretty much everything you would do in Postgres. You can use sequences, default expressions, other stuff, constraints, and you just say using Iceberg. So normally you say nothing here, or you say using heap, but now you say using Iceberg. So you cannot have primary keys on these tables or in other indexes, but you can just do regular insert, copy, insert, select. And then, for example, when there's an update, it'll scan all the well, not all, but scan the Parquet files that might match the filter using DuckDB, find row numbers that match the filter, and it'll write those back into either position delete files, or it'll rewrite the original data files. And then it'll write new metadata files, and then it'll write a record into an internal Postgres table. And because it can actually do multiple of those operations in a single transaction, it can also do multiple writes to Postgres tables and Iceberg tables in a single transaction. So you can, for example, delete from a Postgres table and insert into an Iceberg table, commit or abort. But it's a very simple pattern where you don't have these intermediate states of, oh, I deleted from Postgres, but I failed to insert into Iceberg, and now my data's kind of gone. So that's very useful. And so then when you query the Iceberg table internally, it'll actually, in the pgduck server, send a read Parquet query where it sort of filters, it picks which files it might need, and it filters out all the deleted rows in a join. We're starting to work on doing this for Iceberg v3 as well. So every 10 minutes, some background worker wakes up and it looks for small compact Parquet files that it can merge together. This is quite important to maintain high performance. And then, so yeah, one of the things that pgLake needs to do is try to, when possible, delegate as much of a query into DuckDB as possible, but also in a way that's very transparent, so it doesn't break any SQL. So currently the approach is basically to look, can we take the whole thing and give it to DuckDB? Very often that's the case because DuckDB is very close to Postgres in terms of syntax, in terms of what functions it supports. But otherwise, it hooks into the query optimizer and it kind of starts looking for the biggest section or sections of the queries that it can safely delegate. And so it might see that, oh, there's this query and it looks at like the filters and the projections and the aggregations and the order by, kind of blows up this balloon. And in the end, it finds, okay, this section of the query I can safely delegate into DuckDB. I know there's no functions in here that DuckDB doesn't support. So this becomes a node in my Postgres query plan. And then when that gets executed, like part of that plan is done by Postgres and part of it is done by sending queries to DuckDB and getting the result. And so this way, you don't really have this sort of bimodal thing, which some systems do, where either the query can be fast or it's just horribly slow. Like it tries to make it as fast as it can. And so there's some logic around that of, like, the original SQL query can go through two paths. Either we see, oh, the whole query can be delegated, or we see only a part or multiple parts of the query can be delegated. And then it can, both of those paths end up in the same place where you have a query tree. And then there's a whole bunch of rewriting of that query tree to make the Postgres query tree correspond to the DuckDB sort of function names and function semantics. Sometimes some functions have different semantics around null, or the argument's in a different order, or the name is different. So there's a lot of rewrite rules that we have. And so then we get a DuckDB query tree, parse tree, that we convert into a SQL string that we then set. So you can see, weird transformations, like if you write this in Postgres, underneath it becomes a whole different expression. And so whenever you insert into Iceberg, as part of that insert, we're going to update this internal catalog table. Other engines, I mean, this is, we need to modernize a bit, but other engines can access this directly. Like if you use Spark, you can use a JDBC driver, or for PyIceberg, there's a SQL catalog driver. They understand this table directly, so they can directly access the Iceberg tables. But for us, it's just another Postgres table that a transaction updates. So we can very safely, as I said, delete from Postgres, insert into Iceberg, and commit or roll back. And if you roll back, we also remember which files we generated. So there's a background process that cleans up those files because we don't want to leave them sitting around in object storage. And one of the neat things you can then do, kind of coming back to the small writes. So let's say you have you want your data in Iceberg. Maybe you want to do analytics on Postgres. Maybe you actually want to use this in another system, like Snowflake or another one. But what you actually want is to do small inserts. Like you have lots of different devices just sending individual inserts. And so you cannot do that well with pretty much any Iceberg engine. They're all going to take at least a few hundred milliseconds to do an insert because they have to write all these files to object storage. But here we can create a Postgres table that looks just like the Iceberg table. And many years ago, I wrote an extension called pgcron, which runs periodic jobs in the database. And so you can tell it to, for example, every 10 seconds, delete everything from the Postgres table, and then insert it into the Iceberg table. So you're going to take a batch of data, just sort of flush the queue, into the Iceberg table, do this every 10 seconds. So it's okay if this takes like a second or so, because just, as long as it doesn't take 30 seconds. And so now I can do usually inserts in 1 millisecond into this table. I can probably do like 50,000, 100,000 per second on a large server. And within a few seconds, it flushes into Iceberg, where other systems can read it. And all I had to do was like run 3 commands, essentially. And normally, this is actually a pretty tricky pipeline, because once you've deleted from Postgres, you need to make sure you keep that data somewhere before you insert it into Iceberg. Or maybe you insert into Iceberg first, but then you need to make sure you don't insert it twice. So where do you do that bookkeeping? So, but here you don't really have to do that bookkeeping, because it's just part of the same transaction. But we did find pgcron was a bit limiting for, it's like just running the same thing over and over again. It worked well for queues. It doesn't work in a lot of other cases. So we've built this other extension on top. It's kind of a wrapper around pgcron called pg-incremental. And it basically takes ranges of things. So basically it runs the same query over and over again, but every time it runs it with different argument values. So it will give you a range of sequence numbers, or a range of time intervals, or a range of files, depending on what you want. And then it executes that as a transaction. So slight variation of the previous example, where now we actually want to keep the last 7 days of data in Postgres, because maybe I want to do lookups like, what's the last 10 events that happened to this user or this device? So maybe I have some indexes here. Maybe I do some partitioning, so it can very quickly drop data after 7 days. I create an Iceberg table again. And here's this PG incremental job that says by default, it's every minute. Take all the events between $1 and $2 and insert them into Iceberg. And so these $1 and $2 will take on the value of some range of sequence numbers that you haven't processed yet. And it'll be clever enough to make sure that no ongoing transaction is going to insert into that range anymore. So like the sequence has clearly moved on from this range. And so internally, this also does the bookkeeping of which ranges it's already processed in the same transaction. So now, it's a slightly more sophisticated example. We keep the last 7 days of data in Postgres, and everything is kind of within a minute flowing into Iceberg as well. And I don't need other systems to do that. Can also go the other direction. Let's say I have files showing up in S3, JSON files, compressed JSON files. So I can create a table that points to them. There's this nice file name option, again, sort of inheriting from DuckDB a little bit. And I can say, take all the new files, or files that I haven't processed yet, just as I'll get them as this $1 as this argument, and insert them into my Iceberg table. And again, under the covers in the same transaction, this is going to do the bookkeeping of which files it's already processed. So every file is going to get processed once. And so these are kind of the joys of transactions, that you can build these actually quite tricky pipelines that can have a lot of failure modes, and they become transactions. So if they fail, they'll run again, and we'll just process our backlog, and things are fine. Of course, still want some monitoring to see if it's permanently failing, but other than that, it's pretty simple. Now, yeah, so some new frontiers. Like a few days ago, we kind of added slightly more proper support for using external REST catalogs. Like there's a bit of a challenge for us, because we're a transactional system with the user can send begin, write to Postgres table, and then write to Iceberg table. Now, if we're the catalog, that's an easy thing. But if there's an external catalog, that becomes much more complicated thing, because now it's sort of a distributed transaction. Because I need the REST catalog to commit, and I need to commit in Postgres. So for now, we're mostly recommending, like, if you're using an external catalog, for reads, it works really well. For writes, there's going to be some caveats that we still need to solve. We have thoughts on how to solve them. We're just not super focused on it at the moment, but we will in let's say, within 12 months, I think we'll be done. Or Claude will do it, or Mythos will do it in like a day. But another interesting thing we have been doing, which is like kind of flip the script, where, well, catalogs typically also have a meta store, which is very often Postgres. And so you could actually have a REST catalog that uses Postgres as its meta store, and in that same database also have PG Lake. So you'll find in PG Lake there's a PR, but basically any operation that goes via Polaris will then actually also be applied on the PG Lake side. So a table will pop up in Postgres, and if you write to the table in Postgres, it'll also be reflected via Polaris. And this is still transactional because now the transactions are just sort of properly coordinated by Postgres. There's other things we're working on, like Iceberg v3. A new feature that we've just announced at Snowflake Summit is mirroring. It's not specifically a PG Lake feature. It's more something in our managed service. But basically, the idea there is that we write our change logs, Postgres change logs with updates and deletes into Iceberg tables. We don't immediately apply them to the Iceberg tables because that's very costly. But then we in our case, let Snowflake then apply the changes to Snowflake or Iceberg tables. So yeah, that's it. So what we found is that Iceberg can be a great bridge between these relatively disconnected worlds of operational analytical databases. And with PG Lake, there's a fairly comprehensive v2 implementation, and v3 support is well underway. We're improving our kind of REST scenarios, both using Postgres as the catalog and turning to external catalogs. Some tricky problems to be solved there, but we'll make it work. And so if you want to try it, it's available on GitHub, snowflake-labs/pg_lake. And happy to take any questions.
You mentioned that you synchronize from Polaris to Postgres. Now, are those tables read-only done within Postgres, or do you also support synchronizing back after you updated the table in Postgres?
Yeah, so there's sort of triggers, so they kind of both, and some loop prevention, but yeah, so if you write to an Iceberg table in PG Lake, the metadata will get synced to the Polaris entities table, and if Polaris writes to the entities table, the metadata will get synced back.
How do you deal with concurrent writers?
In the usual way with optimistic concurrency control. I mean, if there's only writers from Postgres, we do more pessimistic concurrency control, but then in the end, we still have this sort of optimistic concurrency control guard that if Polaris did something that conflicts with what Postgres was doing, one of them will roll back.
Other questions?
I have a question. Thanks for the presentation, Marco. So Postgres knows all about the data, so it's a data folder, but what do you know about the data in object storage? Do you keep any state? Do you, for example, for big serial, do you query it every time to increment?
Right. Yeah, I mean, we produce the data in object storage most of the time, if you're writing via Postgres. Interestingly, we don't read normally the metadata that we produce because we actually keep a copy in Postgres itself. So usually queries to Iceberg tables actually can answer in a few milliseconds because like all of the data files that are currently in the table will just be sitting in Postgres metadata tables. And there's functions you can use to see what's actually in the metadata files, and we do a lot of validations to make sure that what we write is correct. Like for things like sequences, they work pretty much how they natively work in Postgres. So kind of an insert goes through a certain path in Postgres where at some point the sequence number will be generated. The state of the sequence is stored just on disk in Postgres. So like there's still like this all the state is here essentially, and in the cloud this will often be elastic block store. Maybe this machine is replicated. So any kind of metadata about what's in object storage, what the table is currently pointing to, is going to just be on a regular disk.
So if you have parallel writes to the object store, then you have to refresh it somehow.
So I mean, if there's parallel writes coming from Postgres, there's going to be like little bit of a serialization point where, like, so inserts can just go like in parallel, and they just need to serialize the commits. Updates, we do pessimistic locking, so we don't really only allow one update on a table at a time, because it's much harder to reconcile two concurrent updates and figure out whether they were messing on with the same data or not and should have actually seen each other. So there we're kind of aggressive. But yeah, so there's also this case where some external engine made an update, and there they use this, there's this kind of last minute validation of, when I started my update, I saw this URL and expected this to still see this URL at the end of my update. If it's not that URL, I'm going to fail. So this is kind of the optimistic concurrency control, where you just optimistically start, and in the end you might actually fail. And pessimistic is just like you wait until.
Then you invalidate your own cache of that metadata.
Yeah. Well, I mean, that sort of gets rewritten under the covers, but yeah.
All right. Fargo, thank you very much.
You're welcome.
Great talk.
Да. А, в этом.
So just 2 minutes to set it up. Или ты можешь просто Studio Restream.
Studio Restream.
Hello? Hello? Так, теперь выключи. Выключи.
Ай.
Теперь делаешь я, entire screen. Whatever you want to present. Entire screen. Теперь стал шерить. Теперь опять рестрим. Yeah.
Is it?
Good to go.
All right.
Okay, finally we can start. Okay, good evening, everybody. My name is Konstantin. I'm a software developer of ClickHouse, and today I want to introduce our features that are related to compactions in Iceberg. I'll introduce 3 features. Like all of them are experimental, but I'm working right now to make them production ready. Yeah, and the last one will be available only in our private repo in our ClickHouse cloud.
Okay, I want to start my presentation from open question. Please raise your hand if you ever had problems with performance for Iceberg table. Okay, 1, 2, great. Okay, in fact, we have a lot of performance issues with Iceberg tables. Let me introduce one example. Like we have such query we select, where, group by, order by, and so on. Yeah, and it's quite slow. If we compare it with our native storage is merge tree, we'll discuss it later, then it's quite slow. Our Iceberg engine is quite slow, and it's around twice slower than merge tree on cold run, and much more slower on hot run. In fact, right now situation is much better because we introduced a lot of optimizations in our previous releases. But yeah, this picture is from winter, I suppose. So why do we have performance issue with Iceberg tables? There are generally three reasons. First of all, is we have a lot of metadata files. If you do, for example, a lot of insert operation, then you'll get a lot of manifest files, a lot of snapshots, and a lot of metadata JSON files. It's quite useful if you want to use time travel features or min-max pruning, but if you do, for example, simple select, then you have to read a lot of unnecessary data, and that's a problem. The second reason is delete files. Delete files is a quite good solution if you need, for example, fast insert operation or fast update operation, but it's quite it's a big problem if you need to, for example, fast writes, because you need to read your data file, you need to read your delete file, you need to some way map them together, and then you need to understand that you don't need to read your data at all. And the last problem is a lot of small data files. Yeah, it's quite a huge problem because it's additional it's additional requirements for our object storage, yeah, and we need to generate metadata files for each data file, so it's also a problem. To resolve such issues, we need Iceberg introduced operation called compaction. If you don't know what's that, I introduced you quite a good picture. Like we have a lot of small data files, and then we do some magic, and we got as an output like 4 data files. They're quite pretty good because they're not big, and that's it. Yeah, a lot of engines introduced compactions, like Spark have compactions. Yeah, the usage is quite simple. Like we need to create our Spark session, then we need to just call this command, and yeah, Spark will reorganize your data files, and yeah, and it will be good. Okay, let's start from our first feature. It's called delete file merge, and what did he do? Imagine that we have a table. The table is like this. So we have one delete file, then we have one position delete file, and then we have a data file. So the problem is those files. I marked it with a red column because we need to read our position delete, and we need to just understand that we don't need to read the whole our data file. So if we want to call compaction for this table, we just write SQL with optimize, it will looks like optimized table and your table, and you'll get such table. In your table, there will be a new data file. I called it a regenerated data file. In fact, it's our data file 1 with applied position delete 1. Then we will have a manifest file and manifest list and a new metadata JSON file. So that's quite simple operation. Yeah, and it's quite obvious how to implement this. That's the whole algorithm. So for each data file, we find position delete files. Then we need to reorganize our metadata. Yeah, we have another one algorithm in our public repo. It's called manifest file compaction. The idea is pretty simple too. Like we have the same table, but we have a lot of manifest files. And for example, if we if we want to just read the latest data, then we need to reorganize our metadata. And that's an example how we can do it. First of all, we can generate a new manifest file. Then we can generate a new snapshot, and then we can generate a metadata JSON file. Yeah, that's the idea is quite simple too. Yeah, and that's algorithm for this compaction. Okay, let's discuss a bit more interesting feature. Please raise your hand if you know what is log structured merge tree. More or less, 1, 2, 3, 4. Okay, quite good. And raise your hand if you use ClickHouse somewhere. Okay, thanks, Rose. Yeah, okay, 2 people, it's quite good. Okay, I'll introduce you basics of our main engine. Our main engine is merge tree. That's our implementation of log structured merge tree. And let's discuss how it works. Imagine that we have 5 operations, like 5 insert in our table. Each operation generates, I don't know how to call it, a directory with data. We call it part. For example, for insert operation, we generate part 0. For the second, we generate part 1, and so on. And each part have own number. It's called block number. Yeah, and what happens next? In the background, we can merge these parts together. Like as an example, we merge part 0, part 1, and part 2 into one part range. It's part range 02, and it has block number 02. Yeah, and we have another merge, like we merge part 3 and part 4. Yeah, and we got another part range, and then such part ranges can be merged into part 0, part 4. Yeah. So that's it. And let's look how it looks like in your disk. Imagine that we have 3 queries, like create table, insert some data. Then your disk will look like this. So you will have 2 parts. The first number is your lower block number. The second one is your upper block number, and the last one is merge level. Yeah, and each part consists of several files like checksums, columns, and etc. And yeah, and there is a main file called data.bin. Also, the main part is the important part is the feature called lightweight updates. So imagine that we have 2 queries like insert and then update the data. So insert will produce your part 0 with block number 0, and update can produce the entity called patch part 0. Yeah, and what does it mean? Patch part 0 says you I have new values for row, for example 10 in part 0, and yeah, and when you do your queries with your image tree engine, then each part then patch part is applied to part, and yeah, and you got actual data. So why do we need to know this? Because mesh tree engine can be is quite similar to Iceberg engine. Like we can replace merge tree parts with Parquet files because yeah, they're quite simple. They're quite similar. Yeah, we can replace our merge tree patch with one data file and one delete file. And yeah, and block number of part is quite similar of sequence number of our part. That's a high level of design of our compaction. Let's discuss in more details. So to build merge tree over Iceberg, we need to answer the following questions. The first of all, we need to understand how to find packet files to merge. In merge tree, it's called parts collector. Then we need to understand when how to choose which groups to compact first. We call it merge selector in merge tree. Then we need to understand how to correctly generate metadata and resolve conflicts. I will explain what I mean later. And the last one is optional, but maybe we need to clear our old files. So in fact, we have three types of compaction. Like we have merge small data, because as I said, it's quite a huge problem. The second one is splitting large data into smaller files. To be honest, I'm not sure that it's quite a useful feature, but Spark has it, and I decided that it's not complex to implement, so I also added it. And yeah, we have the third type of compaction is like apply our position delete files into data files. And about order of operations, be applying positional delete files into data files. So it will be the third type of compaction. And yeah, we need to do this because our position delete files contains information about our data files. And if we do, for example, these two types first, then we will get incorrect data as the result. Let's discuss how position delete file collector works. In fact, we need to build such a graph. Like left side is data files, and the right side are position delete files. And we need to make edges in our graph. So how we can edit? Like we need to understand which position delete files are applied to our data files. And yeah, if position delete file is applied to our data file, we made a link. So what should we do next is like find connected components, and yeah, your connected components will be your set to join, set to merge. Sorry. Yeah, that's it. And we have another entity like data file collector, and it's quite easy. Like if we have one large data file, then it will be one merge group, and we just split it into smaller ones. And if we have smaller files, we collect just n of our files, and yeah, that's our merge group. Yeah, and what should we do if we have conflicts? Imagine the situation that we have a lot of writers, like simple inserts, and we have, for example, a lot of readers, and we have a compaction operation. So the question is, what should we do in such situation? Let me show you an example. Imagine that we have some old table, we have data files, manifest files, and so on, and we produced one compaction operation. Like we generated new data files, new data file 1, new data file 2, new data file 3. We generated manifest files, and we generated new manifest lists. Manifest list contains both new manifest files and old manifest files. And yeah, we want to write new metadata JSON file. But unfortunately, we detect that there was one insert operation. How we can understand this, from example, from our catalog or from version hint file. So we have another insert operation, and we need to resolve such situation somehow, because we don't want to cancel our compaction because it's quite a heavy operation, and also we don't want to cancel our insert operation. So what we can do is just link our insert operation into our compaction operation and regenerate manifest list and regenerate metadata JSON. And yeah, that's it. And the last thing of our design is data cleaner. Like if we produced some compaction, we can notice that we have outdated snapshots that we don't want to use. And we can enable data cleaner, and it will just clean your old snapshots in the background. Okay, let me show you an example how it will work. For example, we want to create a table. The schema of this table is quite simple. It's like 2 columns. Then we specified our engine. It's like Iceberg local. Local means that we use our local disk. We also have Iceberg S3 and Iceberg Azure. And then we specify settings for our compactions, like we need to specify format for our Iceberg engine. Then we need to enable our compaction, and then we need to specify some parameters of our compaction. Then, for example, we need to insert our data, and we will get such situation when we have 4 packet files and some snapshots and some metadata JSON files. Then in 30 seconds, we will have one more snapshot, one more data file, that's it, and one more metadata JSON file. Okay, then we can do, for example, to delete operation, like in this picture. And yeah, we will have additional 2 delete files. We will have some new snapshots, and we will have another 2 metadata JSON files. Yeah, in 30 seconds, we will get one more metadata JSON file. We will get metadata snapshot file, and one more packet file. That's all. Thank you for your attention.
Any questions, guys? A question from my side. Is it all written now in C++?
Yeah, it's in C++.
And it's closed source or open source?
The first 2 features are open sourced, and the last one is in our cloud.
Cool.
Yeah.
And the last one being the cleanup of the data files or the delete file engine? Which one was the last feature again? Which one is
It was about like merge tree with Iceberg engine.
Oh,
Yeah.
So what was the most difficult part to implement?
Yeah, the most difficult part was this conflict resolution, because it's quite hard to test, because we need to do parallel inserts, parallel reads, and we need to just make sure that we don't break our Iceberg table. And yeah, it's quite an annoying part.
How did you test it? Just with like a lot of
Yeah, we have a lot of concurrent inserts, concurrent writes, concurrent reads. Also, we have a check that Spark and Trino can read our tables. Yeah, that's it.
Yeah, are you fuzzing in or how did you create the test? Because I think it's always 10 tests won't cut it properly.
Yeah, we don't have fuzzer yet, but we have plans to do it. But we tested like the most popular Iceberg features like time travel, like partition pruning, and so on, to just make sure that it works.
More questions? Not the case. Then, Konstantin, thank you very much.
Thanks.
And we actually got to the end of the active part of presentation right now, so we do still have a little time till 9.
Yeah, the doors close at 9, so
So
we
1
have,
minute
on
or
the
9.
drinks, and then we'll be kicked out.
Yeah, so use the time till the 9, get a drink and ask for questions about merge tree compaction, PG Lake. It's quite interesting. But I just want to finish it up and say thank you again to providing the venue and the food, and for everyone who was attending today, asking questions, presenting, and see you all next time again. Thank you.
Good.